In this video, I'm going to talk about a few topics that extend the concept of electron configurations to sort of more complex situations. So we're going to consider this topic to be advanced electron configurations. And the two topics I'm going to talk about under advanced electron configurations are how we extend this concept to ions. And in particular, we're looking at what are called monatomic ions. And a monatomic ion is something that it's an individual atom that's charged, as opposed to a polyatomic ion. And the other thing we're going to talk about is something called isoelectronic species. Okay, extending electron configurations to ions is a really simple concept. If we form a cation, we are going to remove electrons from the highest energy orbital. Right, so recall cations are positively charged ions. In order to be positively charged, you need to have lost electrons. So when the atom loses electrons, it's going to lose it from the outermost ion, or outermost energy orbital. Let's look at a simple example. We know that metals form cations, so we're going to use a metal, and we're going to use lithium because that's a relatively simple one. It doesn't have a lot of electrons in it. So lithium has a 1s, 2s, 2p. Lithium has 3 electrons. So it fills through the 2s1. Lithium is in the first column of the periodic table. So when it becomes an ion, it's going to become lithium plus. It's going to lose 1 electron. So when it loses that 1 electron, the one it's going to lose is the outermost one, or the highest energy one, would be the last one you would fill. So now the electron configuration of lithium ion is 1s2. So lithium atom is 1s2, 2s1. And lithium ion is simply 1s2. If you remove more than one, you just follow the same process. You would remove the next highest one. Anions do the opposite, right? So anions gain electrons. So we're going to add electrons to the next available orbital spot. Add electrons to the next available orbital spot. Okay, and so recall anions are negatively charged. In order to be negatively charged, we need to add extra electrons so that the electrons outnumber the protons in the nucleus. So let's look at an example of a relatively simple atom that would become an anion. So we're going to go with oxygen. Oxygen fills up to 4 electrons in its 2p orbital. So as an atom, oxygen looks like this. It's 1s2, 2s2, 2p4. Okay, when oxygen becomes an ion, oxygen becomes O2 minus. We know it gains 2 electrons because it's in the 6th column of the periodic table, so it needs two more electrons to be like a noble gas. So unlike the situation above for lithium where we lost electrons, we took them out. In this situation, we're going to be putting extra electrons in. So for the ion, the electron configuration is 1s2, 2s2, 2p6. What you're going to see over and over again is that when you make ions from main group elements, okay, so these are elements in the S and P blocks as opposed to elements that would be in the transition blocks, the D's or the F's. These are the ones we already learned about. We know how to make ions based on the position on the periodic table. So when ions are made from main group elements, they end up having the same electron configurations as a noble gas. When ions are made from main group elements, they usually have the same electron configuration as a noble gas. So if we go back up and look at our examples above, lithium, if we were to use a noble gas configuration here, would have the same electron configuration as just helium. Oxide ion would end up having the same electron configuration as neon. The reason this happens is that full subshells are particularly stable. Full subshells are very stable. So that's why atoms gain or lose electrons to be like a noble gas, because they're the ones with the full subshells. Okay, let's go ahead and do a couple more examples of this. And I'm going to use some of the problems from number 3 on your electron configuration handout. Okay, here we are on number 3 on our electron configuration handout, and we are looking to make the orbital diagram and full electron configuration for the following species. So I'm not going to go through all of these. I'm just going to go through a couple of them. So we'll do some of the ones we haven't done yet. We'll do nitride ion, N3 minus, and then we'll do magnesium ion, Mg2 plus. So let's start with nitrogen ion, nitride ion. And let's look down at the periodic table here and identify where nitrogen is. Okay, so it's here. It's in the 5th column of the periodic table. To be like a noble gas, it's going to gain 1, 2, 3 electrons. So when we make the orbital diagram and electron configuration, and we're going to start with the orbital diagram. Nitrogen on its own has 7 electrons, so 1, 2, 3, 4, 5, 6, 7. Then when we form the ion, we had to gain 3 more. So those are going to go in the next 3 spaces. And so the electron configuration ends up being 1s2, 2s2, 2p6. All right, let's do magnesium 2+. So magnesium 2+ is down here. And to form, it's in the second column of the periodic table. It's a metal. Metals like to lose electrons and form cations. So it's going to lose 1, 2 electrons and be like neon. So if we come up here and we start with magnesium's electron configuration, it fills through the 3s2, and then it loses 2 electrons. So we're going to lose the 2 3s electrons. So now its electron configuration is going to be 1s2, 2s2, 2p6. The next part of this question says, what do they have in common? Now, we haven't done all of them, but it's pretty obvious that these 2 particular species have something in common with neon, right? If we wrote the noble gas configuration here, this would be neon. And if we wrote the noble gas configuration here, this would also be neon. These all have the same electron configuration. So these all have the same electron configuration, the electron configuration of neon. Species that have the same electron configuration are called isoelectronic. So that's a new term for us. It just means that they have the same electron configurations. Their electrons are the same. They have different numbers of protons. So the nitrogen is still nitrogen, the magnesium is still magnesium, the neon is still neon. That's determined by the number of protons. But their electron configurations are all the same. Okay, so let's review the important concepts from this video. It's important to know that when an atom forms an ion, electrons are gained or lost from the highest energy orbitals. When an atom forms an ion, the electron is gained or lost from the highest energy orbital. And then because we can gain or lose electrons, we can end up with multiple species that have the same electron configuration. And that's called isoelectronic. All right, so at this point in time, you should be able to answer all of the questions on the worksheet that is posted. It's called Chapter 7, Extra Practice. As well as the worksheet that came in the electron configuration handout. So go ahead and practice these skills on those worksheets.